Hello everyone. Now we're going to cover the last case for trigonometric substitution. So case 3 here is when you have like a function f squared minus k squared. So we have again a difference of squares, but the big difference here now is that the equation that depend on x is first. So you have like f squared first minus k squared. So when you have a difference of squares, the first term, so in this case f, is going to be the hypotenuse. And then where does k go? Technically, you could put f as the adjacent side or the opposite side, but if you go back to your right triangle in the sum of square case, k was at the adjacent side, so might as well keep it there. This is going to create the simplest trigonometric substitution. Then, by using Pythagoras' theorem, if you want to compute the opposite side, so it's going to be the hypotenuse squared, so in this case f squared, minus the adjacent side squared, square rooted. And then, of course, remember, this side is a computation, and when you look at the inside of this square root that you compute from this right triangle, it matches the case that you're in. Okay, so remember, the opposite side here is a computation, and the difference of squares that you get inside matches the case. And this is one way to verify that you're on the right path for creating the correct formulas for this trigonometric substitution. So as usual, let's first create a ratio that will link f and theta. So the side that we will always use here is k, so the adjacent side will always be involved in any ratio that we're going to set up. And now we want to link this with f. So adjacent side and hypotenuse, the best ratio here is obviously cos theta. So cos theta will be adjacent, k over hypotenuse f. And that's the ratio that links theta and f. Again, as usual, as soon as you start and create that ratio, that initial ratio that links theta and f, might as well, if needed, construct a formula for theta. So here, by computing the arc cos of k over f, you're going to extract that theta outside of this cosine. And if needed, we have a formula for theta. Now the rest is computational. So the first thing we're going to do is isolate f. So if you swap f and cos theta, you're going to get that f is equal to k over cos. And k over cos is k times secant theta. So that's the formula for f. And now if you differentiate on both sides, so derivative of f is f prime. X is the variable on the left side. And on the right side, derivative of secant theta is secant theta tan theta. And because the variable is theta, you write d theta at the end. So we have a formula for f. Typically inside f, you will have a way to isolate x. And we have a formula for dx by computing the derivative of that equation. And the last ratio that you're going to set up is a ratio for your square root. So now we want a ratio for the square root, which is at the opposite side. And we are going to use the adjacent side as usual. So a ratio that involves the opposite side and the adjacent side is going to be a tan ratio. So here, tan theta, so opposite, f squared minus k squared, square rooted over adjacent. So k, so if you isolate the square root, you just need to multiply by k, so you get k tan theta is equal to f squared plus k squared. All that square rooted, so I just brought the k up here. So under square root, and now we have a formula for the square root. So this is how you set up your right triangle to create a ratio that links that links f and theta. So you can isolate f, you can compute the derivative to construct a formula for dx, and then you can create another ratio using the tan ratio here to link theta and the square root. And this typically really helps simplifying the integral that you're working with. All right, to really assimilate this, let's look at an example right away. All right, so let's compute the integral of 1 over the square root of 25x squared minus 4. So here again, if you think about substitution, by part, whatever, everything will fail. But here, what we see inside this formula, there's a difference of squares. So this is, boom, a case 3 question. And here, your things are being squared. So 25x squared is 5x squared. So your f here is going to be 5x. And the 4 is 2 squared. So when you set up your right triangle, the hypotenuse is going to be 5x and the adjacent side is going to be 2. And then by using Pythagoras' theorem, 5x squared will give you 25x squared minus 2 squared, which is 4. So the opposite side is the square root of 25x squared minus 4. Again, here, this is computed. Okay, and then here I see that the inside of my opposite side matches my case. Okay, so, and remember, this is computed. I'm not sliding this. Okay, so I'm really computing. The square root side is always computed, and it should be thought of a way to verify that this right triangle is well balanced and that it also matches your question. So the first ratio for the function here, so is going to be, so you're going to use, remember, your star side is the adjacent side. So if you want a formula for 5x, adjacent side and hypotenuse are the way to go. So you need to set up a cos ratio. So cos theta is going to be adjacent, so 2 over 5x. And here, this is a good time to compute a formula for theta. So theta is the arc cos. So it's the arc cos of 2 over 5x. So that's my first ratio setup. Now, if I want to isolate my function f, so here there's many ways of doing this, but if you can, you should isolate x. So if you isolate x here, you get that x is equal to 2 over 5 cos, or 2/5 over cos, which is secant theta. So if you isolate x here, you get 2 over 5 secant theta. So when you compute the derivative of x, which is 1, dx, so you get dx is 2 over 5 secant theta tan theta d theta. So we have a formula for x, we have a formula for dx, and then the third step is to find a formula for the ratio. So for the ratio here, I'm going to use the opposite side now, always using the adjacent side. And so by creating the tan theta, by using tan theta, so opposite, so the square root of 25x squared minus 4 over 2. So if you isolate the square root, you get 2 tan theta is equal to the square root of 25x squared minus 4. So we have everything now, okay, for our trigonometric substitution. All right, so let's move things around. So here we want to compute this integral. So if I just rewrite it down here, poof. So we have the integral of 1 over the square root of 25x squared minus 4 dx. So we have a formula for the square root. We have a formula for dx. So I'm going to replace the square root of 25x squared minus 4 by 2 tan theta. And I'm going to replace dx by 2 over 5 secant theta tan theta d theta. And then you're going to get the following formula. So here we go. Boom. Okay, so this will become 1 over 2 tan theta times 2 secant theta tan theta over 5 d theta. And now the only thing I have to do is to simplify as much as possible. So here things do simplify very nicely. So I have that tan theta is simplifying tan theta. There's also an over 2 that simplifies over 2. So you're only left with secant theta inside and 1 over 5. So I will put the 1 over 5 outside. The integral of secant theta. So when you have a trig function alone, you can just refer to your extended basic list. So here, if you use the formula on page 10, poof, the integral of secant theta is ln of absolute value of secant theta plus tan theta. So this will become 1 over 5 ln of absolute value of secant theta plus tan theta d theta. And now I just need to use my right triangle plus c. Don't forget the plus c. Shame on me. Punishment for me later for sure. So here we go. And now using the right triangle, secant theta. So secant theta, well, I like to think about secant theta as cos theta. I know cos is 2 over 5x. So if I want secant, I just need to flip this. So this will become 1 over 5, 1 of secant theta. So it's hypotenuse over adjacent. So it's 5x over 2. And tan theta is opposite, which is the square root of 25 x squared minus 4 divided by 2 plus c. And for that example, actually, that's it. That's all. Okay, so again, everything is rooted in setting up the right triangle correctly. All right, for the third case and the last case for trigonometric substitution, that's it. That's all. Bye-bye.